Yeah, thank you very much. Thank you everyone for joining this session. So during this talk, I'm going to show how it's possible to operate your Kubernetes workloads using the operator pattern. So how it's possible to extend the platform, so the Kubernetes platform using the operator pattern, and see how to handle the workloads on Kubernetes. Let me introduce myself a little bit. I am Paolo Patierno. I am a principal software engineer in Red Hat. I work on the team which is about Kafka and Strimzi. And Strimzi is an open source project about running Kafka on Kubernetes. So I am one of the maintainers of this project, which is under the CNCF Foundation. I am also committer for different projects under the Eclipse Foundation, mostly related to the IoT stuff and Vertex. And I am also Microsoft MVP for the Azure technologies. In my spare time, I mostly love to run, swim, and even following motorsports like MotoGP and Formula One. So let's start since the beginning. So let's try to introduce a little bit Kubernetes. People knows that Kubernetes is a platform that really helps you to automate the deployment of your containerized application, but even the scaling and the overall management of this application. So we are talking about having your application containerized and then running on Kubernetes. Kubernetes can also be defined as a kind of Linux kernel, but for distributed systems. Why I'm saying this kind of thing? Because you have your own cluster with nodes that can be bare metal nodes or even virtual machine, and you can install Kubernetes on top of it. With Kubernetes, you have a kind of abstraction layer on your own hardware. So you don't have to take care of the hardware anymore. When you want to run your applications, you can just containerize your application, submit to Kubernetes, and we will see in a little bit, thanks to the scheduling, Kubernetes will find the right node with the right resources in terms of CPUs and memory for running your application. So in this way, you can even move your application across different Kubernetes instances. So you can start having your Kubernetes even on your local laptop with Minikube, for example. Then you can move to your Kubernetes instance running on a data center on your own, or even running the same application on Kubernetes in the cloud. So on some cloud providers that provides their own service with the Kubernetes instance running. So it also facilitates the developing of a hybrid cloud solution when you can have your application running on different Kubernetes instances across different clouds, right? But let's see a little bit of more about Kubernetes. What are the main features that you get from Kubernetes? So as you already mentioned a little bit, it's about container scheduling. So you have your application, it's any container, you submit your container to Kubernetes, and Kubernetes will find the right nodes when there are enough CPU and memory for running your application. So there is a component which is called the scheduler doing that. But Kubernetes also helps you for self-healing. So it means that if your application crashes, for example, for any kind of problems or maybe bugs, you don't have to do manually your work to start up the application again, but Kubernetes, using some so-called probes, can detect that if your application is ready, is live, and then in that case, it can restart the application if it's not responding to these probes. So it's something that anyway you have to develop on your side in order to support the probes for your application. But Kubernetes will help you on this. It also helps for discovering your application. So if your application should be should be reachable from other applications running on the same Kubernetes cluster, or even from the outside. In general, you have a service in front of your application instances, if you have one more than instance, and the service will help the other application or clients outside of the Kubernetes cluster to reach your application, even handling the load balancing. So it means that when you have more instances of your container running, the service will spread the traffic across all the instances. And it helps also for the horizontal scaling, because if you have different load of traffic in different times, Kubernetes can help you easily to scale up and scale down your application if you want to handle more traffic or less traffic. It depends on the times sometimes, right? And that can be done easily on your side or even automatically by Kubernetes itself. Other than this, there is a specific feature for handling configuration, like using config map for people who already knows about Kubernetes, so for storing the configuration for your application, or even things like TLS certificates in the secrets. The other things are like, for example, the storage. So if you need that your application needs some storage for storing data, or even the automated rollout and rollback. So if you upgrade your application to a new version, but then, for example, at some point, you can do even a rollback if you find some bugs that you want to come back to the previous version. Last but not least is about batch execution. So if you want to run some jobs at specific times in your platform. So these are just a few of the services that Kubernetes provides. But in general, when we talk about workloads in Kubernetes, what are we talking about? I already mentioned containers, because Kubernetes is a platform for orchestrating the running of the containers, right? But the unit of deployment in Kubernetes, it's not just the container, but it's the pod. You can see a pod as a set of containers. In general, you have just one pod with one container, but there are even use cases where you can have more containers in the same pods. Think, for example, about the sidecar pattern, where you have in one pod your main container with your own application, and then running a sidecar, so another container which is improving, helping, or adding more features to your main application to do its stuff. So in this case, you have two containers in the same pod, but in general, you have just one pod with just one container inside of it. So developers can use the pod, right? So in Kubernetes, you have this built-in resource, which is the pod, that you can describe with a YAML. You can define the configuration, the probes, the container image to use. But if using pod, how Kubernetes handle things like the scaling, the rollout, the batch execution, so all the other things that I mentioned as the main features that Kubernetes provides to you? Well, of course, just using pods is not possible. This is the reason why mainly in Kubernetes, developers don't use directly the pods, but they use some more sophisticated resources. Just mention two of them: the replica set and deployment. For example, with a replica set, you have the guarantee that a specific number of instances of your application are running. If you want to do this on your own using pods, for example, having, I don't know, 3 instances of your application running, you have to create 3 different pods with different name, but pointing to the same container images, with same configuration and things like that, right? Which is not so simple then to handle the scale up or scale down, because you have to add a new pod, you have to delete a pod, etc. With the replica set, you are facilitated on that, because you can specify the number of replicas, you describe as a template the pod that you want to run, and with the replica set, Kubernetes will take care for you of having the right number of pods running. So spinning new pods if they are not enough, or deleting pods if there are too many. And we will see in a little bit how it really works. The other one is the deployment. The deployment is a kind of new abstraction layer on top of replica set. So it's a new resources that it's using a replica set for running replicas, but then it adds a new layer for doing things like rollout and rollback. So if you want to, for example, update your application to a new version, so the deployment will be able to so Kubernetes through the deployment will be able to start up a new replica set with the new version of your application, and at some point shut down the old replica set with the previous version. But because it takes an history of the replica set, it's also possible to do a rollback. So if you find a bug in your application, you can just roll back to the previous version. So all the kind of things that a replica set and deployment helps, and you don't have to do on your own just using pods. There are many other more resources in Kubernetes for handling workloads, like the stateful set, which is kind of similar to the replica set, but it's used for a stateful application, while with replica set, it's mainly for stateless application. Then you have job, if you want to run some tasks at specific times, like for example on Linux you use the cron jobs. You have the daemon set resource for running some tasks as a daemon, so always running on all the nodes of your cluster. So in general, you don't use just the pods, but you use all these more sophisticated built-in resources that you have in Kubernetes. But say that, how does it really works? So how specifying and describing your replica set, your deployment, you have this kind of automation in Kubernetes helping you to run your application and handling the kind of the life cycle of your application. Well, the main concept that handles this is the concept of the controller. Of course, it's not the one which is into the picture. But in this slide, you see the so-called control plane. So the main components that make the control plane in Kubernetes. You see the API server, which is an HTTP REST server exposing different endpoints. And this is the server that we interact, for example, when we use the kubectl command line tool for creating our pods, our replica sets, our deployments, for creating all the Kubernetes resources that are available in Kubernetes. So you create your YAML describing your resource, and then you submit to the API server, where the command line tool is just interacting with some HTTP endpoints where these resources are exposed by the API server. So the API server is storing these resources in etcd, which is used as a kind of key value store. And then there is one another main component that I already mentioned before, which is the scheduler, where when you submit the creation of a pod, the scheduler will check that the resources that you are asking for, if you are describing the CPU and memory in your pod description, are available, and then it will find a node and then schedule the pod running on that node. But other than these three components, because we are talking about automation in Kubernetes and how things like replica sets and deployments works, the main component is the controller manager. So in the controller manager, you have one or more so-called controller. Each controller is in charge to handle one of the resources that I mentioned. So there is the replica set controller, for example. The controller is actually an application, so it's a container on its own, which is using the API server, is interacting with the API server, because it's watching and it's getting some notification when, for example, a resource is created or changed or deleted. And then the controller is still interacting with the API server for doing some other operations, maybe creating some other Kubernetes resources. So it interacts with the API server to do some creation, patching, or even listing if the controller needs to get information about some other resources in Kubernetes. So this is the component that allows to things like the replica set and deployment to work. What's the main job of the controller? So the controller works in general in this way, following a so-called reconcile loop. So the goal that the controller has is about making sure that what it's described in your resource, maybe through the YAML, is matching with the state that you have on the Kubernetes cluster. So it means that in this loop, it's observing. So it's using the API server watch on the endpoints to check that a new resource is created or is changed, or maybe it's deleted. It analyzes, so it's check if what is the difference between what you are describing in your YAML, in your resource, in your object, and what it's actually the state on the cluster. So if, for example, for the replica set, actually the 3 replicas that you are asking for are running or not. And then it acts somehow. So it applies some changes or interact with the API server to make this real. So to have the match between the description of the resource with the current status of the Kubernetes cluster. And this is the loop where the controller works. So the so-called reconcile loop. But for making this clear, let's see how it works for a replica set, for example. On the left-hand side, you have a replica set definition with the name. You have the template. The template is actually the template of the pod that it's going to handle for you. So with the spec, the image of your application, a label. Then you have the selector. It means that using this selector, the replica set will take care of the pods matching that label. And in this case, it's obviously matching the labels in the template. And you also specify the replicas. I want 3 replicas for this. So for this application running on my Kubernetes cluster. When you create your replica set this way, the replica set controller will be notified because it's watching. It's in its reconcile loop to observe, and it will match that. We'll see that there are no pods running on the Kubernetes cluster at the beginning, matching this criteria. So it will spin up for you 3 pods. On the right-hand side, you can see the 3 pods. The name is, in general, the name of the replica set plus some hashing. So it's starting up the 3 pods actually for you. You don't have to do that on your own, right? But if at some point I want to, for example, scaling, so doing a scaling up and changing just the replicas number from 3 to 5, in its reconcile loop, the controller again will see that the reality on the cluster is 3 pods running, not 5. So it will spin up 2 more pods in order to match what you are describing, what you want about your application through the replica set definition. But let's make another example. Let's assume, for example, that when we have just 3 pods running with 3 replicas, I'm going to create 2 pod resources with the same label of the one which is in the selector of my replica set, with the same description of my application. So it means that the replicas, in this case, matching the selector, will notice that there are 5 pods running while you are asking for 3 in the replica set. So it's going to kill the 2 pods that you started, right, manually, using just the pod custom resource, because you are using the same label matching the selector in the replica set. And what happens in the other way around? So let's assume that from a clean situation, I create 2 pod instances with the same label, which is my app in this case, for my application. And after that, I create my replica set, asking for 3 replicas. The replica set will start to take care of all the pods matching that label, which we have defined in the selector field. So it means that it will notice that we already have 2 pods running, even if they are not created by the replica set, but manually by you using the pods. So it will spin up just 1 more pod in order to match your request, your desire to have just 3 replicas running. So this is how the replica set controller works, how the magic, the automation of the replica set works, thanks to the concept of the controller. But it will be great if something like that could work for our more complex applications. So thinking about, I don't know, things like Kafka, just to mention the project where I work on. When you have Kafka, you have to deal with the Kafka brokers, the zookeeper ensemble, or things like upgrades, updating the version of Kafka. So there is a lot of complexity around Kafka. What if I want to have something like this automation on a Kafka cluster? This is where the operator pattern comes into the picture, where this pattern was introduced by CoreOS in the past, which is now part of Red Hat. And it's about adding the business knowledge of your application in an operator which is not a human anymore doing the job manually, but it's a software operator. So as I mentioned, an operator in the operator pattern is a application itself. So it's a container running on the same Kubernetes cluster where you want to deploy your complex application. It has the knowledge about your specific business domain. So an operator handling Kafka has the knowledge about Kafka, how Kafka works, how the upgrades works on Kafka, the security works on Kafka, and all the things like that. So the operator is able to handle the entire life cycle of your application, right? It leverage a kind of extension point in Kubernetes, which is called the custom resource definition, which is a way for extending the API server. It means, and we will see in a little bit, that the Kubernetes cluster, the API server, will start to understand not just the built-in resources like pod, replica set, but more custom resources which are related to your own application. We will see more in a few. So an operator, how the operator is related to the controllers that I introduced before by talking about the replica set, for example, because an operator will be made by one or more controller, and each controller will take care of one custom resource, which is related to your business domain, your specific application. Then the operator will do some work for you, will, for example, create or handling in general the corresponding Kubernetes native resource for having your application running. And we call them the so-called operands. So let's see how this operator pattern is able to extend the overall Kubernetes platform. First of all, back to the picture that we already saw before, we extend the API server using the so-called CRD, so the custom resource definition. So we are describing a new custom resource, let's say a custom resource named foo. So in this way, the API server and Kubernetes in general, we know about not just the pod, the replica sets, the deployment, the stateful set, so all the built-in Kubernetes resources, but even your custom resource. What is foo? So it will have a new endpoints for interacting, for handling, creating, and things like that, the new foo custom resource. So with your command line tool, you can create your custom resource. The API server will be able to store the custom resource description in etcd, but then on the other side, you have the operator with a corresponding controller that will do the kind of the same work that we have with the replica set. So it will be in charge to watch your custom resource and following the same reconcile loop. So to do some work when a new custom resource is created or is patched or is deleted, right? In general, it can be or creating some operands, so interacting again with the API server to create some, you see on this slide, deployment, config map, PVC for storage, or it could even be just interacting with an external service. So your controller in the operator will not do anything on the Kubernetes cluster. There are some operators, for example, for handling Azure services or AWS services. So you create a custom resource describing your Azure service, and then this operator will just do something with the external service on Azure. But it can, in general, the operator will interact again with the API server in order to create some Kubernetes built-in resources, so the so-called operands. For making this clearer, let me introduce Strimzi as an example. So, as I already mentioned before, Strimzi is an open source project which is part of the CNCF Foundation since September 2019. And it's about running Kafka on Kubernetes. So it provides some container images for Kafka, Zookeeper, and other components, but mainly this project provides some operators. So not just one. The main one is the cluster operator for handling your Kafka cluster, so for deploying it and for handling the entire life cycle of the cluster, but even some other operators for handling the main things in Kafka, so the users, the topics, but there are also features for handling the other stuff that we have in the Kafka ecosystem, like Kafka Connect, Kafka Mirror Maker. There is also integration with the cruise control for the rebalancing. There is also a bridge for accessing the Kafka cluster via HTTP. So there are a lot of things that this operator will take care for you. So it provides a kind of Kubernetes native experience for people who want to run Kafka on Kubernetes. They should not know much more about Kafka, but more about Kubernetes, because they are handling the Kafka cluster in a really Kubernetes-oriented way. So how this operator works in terms of what I mentioned before, so extending the API server, then having the controller, what does it mean really? First of all, you have a new custom resource definition. So on right-hand side, you can see the Kafka, a new Kafka kind. So you have a new custom resource defined in your cluster, in your Kubernetes cluster. So you can see there is an open API specification where there is the spec or the fields that you have in your Kafka custom resource, the status that you should expect to get back from the operator. So you are describing a new resource. Kafka becomes a native Kubernetes resource. The Kubernetes cluster and the API server mostly will be able not to understand just the pod, replica set, and things like that, but even Kafka with a specific endpoint. Of course, it means that you need someone to handle the Kafka custom resource. This is where the controllers inside the operator will work. So on the left-hand side, you can see here a Kafka custom resource. I will check this in a little bit during the demo, but you see there is a custom resource with a kind Kafka and with some description. I am describing my Kafka cluster that I want to deploy on my Kubernetes cluster. The controller in its reconcile loop will get that there is a new Kafka custom resource be created and will act on that. So it will start to create some other Kubernetes native resources, so the operands. So a stateful set for the Kafka brokers, another one for Zookeeper nodes, the config map and secret for configuration of the brokers, for TLS certificates for security, the PVC for storing the messages in Kafka, the network policies for defining the permission for accessing the pods, all the things like that. So they are all handled for you by the operator, the controller inside the operator. So there is no need for a human operator creating all this stuff on the right manually and then taking care of them for having the Kafka cluster up and running. The user has just one custom resource, the Kafka one. It will be the source of truth. And the operator will take care of handling all the stuff on the right-hand side. It's also true that if you try to change something in the stateful set, in the config map, they will be reverted back by the operator because the source of truth is the Kafka on the left-hand side. So you could ask how this works compared to the Helm charts, right? Because a lot of people use the Helm charts for running your application on Kubernetes. Well, when we talk about Helm charts, we are really talking about a package manager for Kubernetes. So a chart is made by a template and values. You are describing your application using the Kubernetes built-in resources, so using the deployments, the config map, the secrets. You have a YAML as a template with some placeholder, and you have a values, so a file with the values to fill this placeholder and deploy your application really easily. It's simplified the day one operation, which is about deploying your application, right? So you can easily deploy your application, so the same application with a different configuration, because you can have just to change the values using the same template, or running the same application on different environments. The main difference with an operator, so talking about the operator pattern, is that with an operator, you can handle the entire life cycle of a Kubernetes workload, of a Kubernetes application. You have this extension point using the CRD, the custom resource definition. You have the controllers for handling this new custom resource. So what you do is just writing some few, one maybe with the Kafka custom resource, for example, in Strimzi, custom resource, corresponding YAML, and then everything on the other side will be created and handled for you by the operator itself. So it's not about handling the deployments, the config map. It will be done by the operator. You have just to write your own custom resource. So it helps you with the day one operation on deploying, but even the day two for handling upgrades, security, and all the kind of things. Because when you change your custom resource, the operator will operate accordingly. But these two words can live together because an operator in the end is an application running on Kubernetes. So you can deploy an operator using Helm chart. There is in the Helm charts, there is a feature interesting because the Helm chart guarantees that the CRDs are installed before an operator, otherwise an operator cannot work without the CRD, of course. And you are also able to configure your operator if you need some parameters, configuration parameters for your operator, using values, using a config map. So it's really a way for using the best of the two different worlds. Helm charts for deploying the operators and the operator for handling the entire life cycle of your main business application. But yeah, I have talked a lot, so let me just show you a demo about this running. So as you can see here, I am using Strimzi as an example. I have my Kubernetes cluster running on Minikube. I have my Strimzi cluster operator up and running. Let's see what I have here. What I have here is a description of a Kafka cluster. You can see this kafka.persistent YAML file. Let me just create the YAML file first in the Kafka namespace, and then we will see in a little bit what is the description that I have inside. So I am creating my Kafka custom resource. The operator will start to take care of it because it's listening, it's watching, and then it will start the corresponding pods inside our application. So at some point, we should see that the Zookeeper pods are running, and yeah, the cluster operator detected that a new Kafka custom resource was created, and it's starting the Zookeeper pods in our namespace. So while it's starting up, let's take a look at the Kafka YAML. So you see here that what I'm describing is a new custom resource, the kind Kafka. There is a specific section about the Kafka. So I am describing my Kafka cluster with the version of Kafka I want to use, with the number of brokers that I want. There is the list of listeners. The listeners are used for exposing your Kafka cluster to the other application. So to clients that are running already in the same Kubernetes instance or outside. So you can enable TLS, for example, all the things like that that are in the Kafka concept, right? Then you have the configuration of your Kafka brokers. So this configuration will be applied by the operator or all the brokers running on your Kubernetes cluster. You can specify the storage. In this case, I am configuring a JBOD persistent storage for running my Kafka cluster. There is also the section for Zookeeper, for running the Zookeeper ensemble, even if today it's going to be not used anymore with the new craft mode for Kafka, and that it will be supported in the future by Strimzi. It's on our roadmap. The latest thing is about running the two more operators that I mentioned, the topic operator and the user operator for handling the topics and users in your Kafka cluster. So what you're doing is not actually defining any things like deployments or things like that. You are just describing your Kafka custom resource. And as you can see here, everything is starting. I have the three Zookeeper nodes, the three Kafka brokers, the entity operator with the user and the topic operator are started. But what the operator did for us, so if I, for example, get the stateful set from the namespace, you can see that we have the two stateful set for our Kafka and Zookeeper brokers. We can check, for example, the config map. Even in this case, there are the config map with configuration for brokers, for the topic and user operator. We also have different secret for handling the TLS certificates. And for example, finally, we can see also the PVCs, so the persistent volume for storing the messages. So everything was created by the operator for me. But other than deploying, like for example, I want to handle an update on the on my Kafka cluster. So I want, for example, do some configuration change. So let me change my cluster Kafka. So I have to edit my Kafka custom resource. If I want to change the configuration of my Kafka brokers, what I can do is just maybe, let me say, adding the retention hours for my messages from 7 days, which is by default, to 2 hours. I'm going just to change this configuration, and then the operator will detect my change, and in a little bit it will start to do the rolling update of the pods. So you can see here this pods is rolling, and it will restart in a few. Right, so it's rolling for me all the pods one by one. It's something that in general you should do manually, somehow upgrading the configuration to all the pods, all the brokers in Kafka, but the operator is taking care for you to do this. And it also has the logic about, for example, rolling the Kafka controller as the latest one, which is important for high availability of your cluster, of your Kafka cluster for clients. And it's also not rolling all the pods all in one shot, right? It's doing the right operation, rolling the pods one by one on its own for you. It's also true if I'm going to change the replicas in my Kafka custom resource because I want to scale up from 3 replicas to 5, the operator will take care of that, doing the same. So going to spin up 2 more brokers for you, and configuring the brokers with the right configuration for you. So this is how an operator works, handling a more complex application by using the controller thing, which is something that it's built in somehow in Kubernetes that we will use, even if maybe we don't know, but we will use every day when we deploy a replica set, for example. Now, let me come back to the slides just for giving more few information about the operator world. So one thing is, if I convinced you how to start to use the operator pattern, of course you should write your own operator. What's the way for writing a new operator? So there are 2 different SDKs for doing that. If you prefer to write the operator using Golang or using Java. The operator framework is a tooling for developing Kubernetes operator in Go. So if you are a Go developer, it provides all the boilerplate code that you need for actually getting notification about custom resource, where the custom resource is created, is deleted, or is changed, so that you have to just to focus. So for handling the reconcile loop, what you have to focus on is just focus on writing your logic, the controller logic, which is related to your business logic. So in my case, for example, the Kafka logic, how a Kafka cluster works. But the operator framework also provides a component called OLM, the Operator Lifecycle Manager, which is an operator for handling operator, because in the end, operators are application, they are versioned, there are new version with the bug fixed, and if you want, you can upgrade your operators, of course, and even doing rollback. There is also a registry which provides some operators, and if you have OpenShift, which is a Kubernetes distribution by Red Hat, you have this catalog of operators out of the box. Other than this, if you have a Java developers, there is the Java Developer SDK. It's kind of new, but it's growing a lot. During the last years, it has had a lot of improvements. And one of the interesting things is that for people who knows about Quarkus, it has a Quarkus extension. So Quarkus is a Java stack for writing Kubernetes native application. So it means that you can use all the Java libraries, the Java standards, but mostly focused for writing a containerized application running on Kubernetes, for having better performance, even using low memory and things like that. Even because other than running your application in a JVM, you can run it as a native mode. So you can build the native container images using Quarkus, using GraalVM, which is part of Quarkus. Say that you will have your operator with best performance for handling more custom resource. Where you can find operators, there is this operatoropp.io website where there are a lot of operators in different categories: database, messaging, networking, and things like that. There is a Strimzi, of course, there. You have the Helm charts or the YAML files for easily installing them on your own Kubernetes cluster. And if you want, you can also, you can develop your own operator. And if you think that it's useful to the community, it will be great that you could submit your operator to the community and having it available on the operatoropp.io. Say that these just a few links to some resources for for having more information about everything I mentioned during this session. So information about the operator framework in Go, the Java Operator SDK to start writing an operator, operatораpp.io for searching for maybe some operator that you need today to simplify your deployment, the Strimzi operator for Kafka, the Kafka documentation, and the simple demo that I just showed to show you how a real Strimzi, a real operator works. So Strimzi, you have here the link to the demo for trying that on your own laptop. So yeah, thank you very much for joining, and yeah, I'm here if there are any questions.